To calculate jump height, we'll be using the equations of constant acceleration. In second year, you used these equations to work out jump height, but you use the impulse-momentum relationship to calculate the velocity at takeoff. We're going to do it slightly different this year. We're going to use time in air to be able to calculate the height jumped. And the equation we're going to use is S is equal to ut plus a half at squared. And S is the displacement, t is the time in the air, and a is the acceleration due to gravity. So to work out the time in the air, we need to know when the person is in the air. So if we scroll down along, looking at the column N, which has zeros at the beginning, indicating they were in the air as they came to land on the force plate. And as we scroll down along, we'll see numbers kick in. These numbers are telling us that ground contact was made. Then, after a short time, the numbers go back to zero again, so they're in the air again. And this is the time that they're in flight on the second jump, and then the numbers appear again. So we need to know how long they're in the air. And the way we're going to work that out is we're going to say that this cell here is equal to the touchdown time, which is this one here, less the takeoff time, which is this one here. So it's the first and last one with numbers. So that's the time they're in the air. So for this particular trial, they're in the air for 0.36 of a second. Now we're going to use the equation, which is kind of the equivalent of dropping a ball. And we're actually going to look only at the time it takes to come down again. So I'm actually interested in a half of the time, because they'll be up at the top of the jump halfway through that time. So this one here is going to be equal to the time divided by 2. Now, because halfway through the jump you're at the apex, you're at the top of your flight, you're going to have zero velocity. So while the equation is S is equal to ut plus a half at squared, because u is 0, we can say that's also equal to 0. So we use the equation S is equal to a half at squared. So the next thing I need to do is I need to say this is equal to that number squared. Okay, and I raise it to the power of 2, or you could just multiply it by itself. So here I have time. Here I have time over 2. And here I have time over 2 squared. And then the next thing I need to do is I need to work height jumped. So I'm going to say this one is equal to 0.5 multiplied by gravity, the acceleration due to gravity, which is 9.81, multiplied by a half at squared. Okay? And that gives me a number. So for instance, for this jump here, the jump was 0.158922 meters. So we'll round that up to 0.16 meters or 16 centimeters. So that's how high the person jumped. And I need to do that for all of my participants in the trials that I'm selecting for analysis. The first thing you do is you find the time. We find the time. We find the time by subtracting the touchdown minus the takeoff. We half it, we square it, and then we find the flight by saying S is equal to a half at squared. And so you should be getting a number somewhere between 10 and 30 centimetres. I'd be amazed if they jumped that high. They should be probably jumping somewhere around 15 to 20 centimetres. So 0.15 of a metre is 15 centimetres.